Notes 2, Radioactive Decay and Half-Life. I would repeat this one a few times. Make sure you practice, 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 because radioactive decay and half-life problems is usually where a lot of people lose points. Okay, the first thing you want to do is just memorize the symbols. So for alpha, it's going to look like this. So anytime you see this is alpha, or it will be in helium atom. Gamma usually looks like this. That's how you know you have gamma. A neutron is going to look like this. Proton, and the beta particle is going to look like this, or that. And yeah, so we'll just learn by doing. So here's an example. So we have uranium, radioactive uranium. We know that it's radioactive, so it means that the nucleus is going to undergo transmutation of some sort. Okay, so say this is what you have, and you want to figure out what kind of particles you have. You would just label, okay, I have an alpha, so I know I have alpha decay. We know we have gamma. Okay, and then another thing I could ask you, is it balanced? So let's check. Let's see. It has to be balanced because we can't create or destroy matter, even though we're getting rid of things here. So it's 238. It's on the top. 234. So we have 238 equals 234 plus 4. Okay, so that works. Now let's check the bottom. 92 equals 90 plus 2 plus, let me add a 0. So we see that it is balanced, so that is correct. So something I could do is give you the wrong mass somewhere or the wrong atomic number, and you would have to correct it. Okay, let's do another one. Alright, so this is what we have. So we look at the top, these are equal 0, -1, 91, 90, so we know we have a beta particle being released here. So this is the form of radioactive decay we have is beta. Okay, so a lot of times with these type of problems, what I'll do is remove one of the elements. So I could have not had TH here, PA might have been missing, and you would have to fill in the blank. You could have mass missing, etc. Alright, so let's do something like that. So the first one, alright, so here we need to look at our equation. Let's see, what are some things we notice? We notice we have an alpha particle, so we know this is alpha decay. So first now we need to check to see if we're following the law of conservation of matter, which says we cannot create or destroy matter. So we started out with 209 as our mass. So that's telling us the number of protons and neutrons. So let's see, what should we have on this side? We have 209, and it's supposed to equal something plus 4. So what is that x going to be? 209 minus 4, it gives us 205. Okay, so let's check the bottom. So we have 85 is the atomic number. Let's call it y plus 2. So y has to be 83. So now what we want to do is look on our periodic table and figure out what element we transmuted. Because remember, this is a transmutation. Okay, so after looking on the periodic table, we notice we have Bi for bismuth. So we created bismuth from astatine. So this could have, this was probably most likely a natural transmutation, because remember, for artificial transmutation, we would have to take a nitrogen particle and ignite or permeate the atom to make it unstable, and that would cause the reaction. But for this one, it's going to be natural. Okay, let's look at another radioactive element, or atom, excuse me. Okay, this is what we have. So what we want to do now is look at our mass. So we have 14 equals 0 plus x. So we know x has to be 14, so nothing changed on the top. 6, so we have 6 equals negative 1 plus y. So our y, which is going to be our atomic number, has to be 7, because 7 plus negative 1 is 6. So we look at the periodic table and figure out which atom has an atomic number of 7. Alright, and what we get is N for nitrogen, and that is the correct answer. Okay, so, well, there's one more thing we could have. We know that this is beta, so we know this is beta decay. Alright, so that made no sense. Just repeat it a few times, sit with it, go look at the study guide, go back to the lecture, but if you go through it a few times, I'm sure you'll get it. Alright, so let's move on to half-life problems. So on the screen I have the half-life equation, but we're not going to use that for this one. I'm actually going to show you a different way to do it. So this problem is saying an isotope of silver has a half-life of 10 minutes. What fraction of the original mass will remain after 1 hour? Okay, so we know the final time is an hour. The half-life is 10 minutes. So what I would do for this one, seeing that it's just asking us for the fraction, is to think about how many half-lives have occurred. So in 60 minutes we have, there's 1 half-life, 2, 3, 4, 5, is that right? 10, 20, 30, 40, 50, oh, we're missing one, 60. Okay, so half is divided in half 6 times by now. So if we multiply all of these, 2 times 2 times 2 times 2 times 2 times 2, which is basically 2 to the 6. When we do that, what do we get? If you don't have your calculator, go find it. And I would use a basic calculator because these phones, these touch screens on these phones just sometimes will lead you astray. And when you do that, you should get 1 over 64. So this is the fraction that is interested in, because it's saying what fraction of the original mass. So that's how much of the original mass would be left. So if we wanted to elevate this question, I could tell you what the original mass was, and then you would tell me what the final amount is. So this equation you plug here. Now, if you don't like this method, you can use this here. You can plug this in and figure out this fraction here. But this is a different way of doing it. Alright, so I have the equation on the slide again. Again, I'm just showing this to you, but you don't need it for this question. But there are some others that will pop up that you will need this equation, but I have it there so you can familiarize yourself. But the question says you find a rock sample with radioactive atoms present. Is 25% of the original radioactive atoms were present? How many half-lives has the rock been around for? It's a weirdly worded question. I should have edited. Oh well. But the question is saying that you have 25% left, so that's that final amount. And you started out 100. Okay, so because you're talking about you're basically trying to date the rock. So you probably would have used some type of carbon dating here. But if we think about it, if you start out with 100% and you divide it by 2, you undergo 1 half-life, you get to 50%. Then you divide that by 2, you end up at 25%. So that happened 2 times. So your answer would be 2 half-lives. Okay, this time we're going to use the equation. So I've been meaning to say that this is the same equation from class. So A equals A sub 0. I'll just rewrite that. This is the same equation. The only difference is that we just move the 2 that's down here over. So we just, like, if I move it over, you see, now you can see that they're separate at the end. And then right here we have time divided by half-life. Remember I said n is the number of half-lives. When you take time and divide it by half-life, it tells you the number of half-lives. So for example, if you wanted whatever that final time is and divided by the actual half-life, it tells you the number of half-lives. So it's the same thing. But anyway, so how much of the 95.6 milligram sample of thorium-230 with half-life of 8,000, this should say years, would remain after 32,000 years? So let's plug it in. I always like to just rewrite the equation, just kind of a habit thing. And I'm going to plug it in both equations just to prove my point that they're the same. But we're looking for how much of the sample will remain. So we're asking for the remainder, so we're looking for the final. So we know the original. Okay, the time that has lapsed is 32,000 years, and the half-life is 8,000. Okay, so 32. So I'm going to first reduce this so we know these zeros cancel. So 32 divided by 8 is 4. So that is the number of half-lives, so 4. So now I'm going to multiply everything. 0.5, raise that to the 4, multiply by 95.6. Okay, we get a final answer of 5.2. 975. Okay, I'm gonna use the other equation just to show that it's the same. Okay, this one you would need to figure out the number of half-lives. So for this one to work, we would take our 32 divided by 8, we get 4, so we end up with 95.6 divided by 2 raised to the 4. We plug that in the calculator, and we end up getting the same thing. Now, alternatively, you could do this without the equation. So what you do is that it takes 4 half-lives, so you can just keep dividing it by 2. Get the answer, divide that by 2. Get an answer, divide that by 2. Get an answer and divide that by 2, and then you should get 5.975. So that is an alternative way of doing that if you don't want to use the equation. Alright, so practice makes perfect. Let's practice. Well, we don't have any more but on this slide, but practice in the study guide.